Hi, everyone. Welcome back. My name is Ariana Forsyth, and I'm the chapter president of ESW at UT Austin. It is my pleasure to introduce Dr. Carey King. He is a research scientist at the University of Texas at Austin and the assistant director of the Energy Institute. He performs interdisciplinary research related to how energy systems interact with the economy and environment, as well as how our policy and social systems can make decisions and trade-offs among these competing factors. During the presentation, you can add questions to the Zoom chat, the global Slack channel DigiCon2020, or text the number that you received in the email that I can also leave in the chat. After Dr. King is finished, we will use also the Zoom raise hand function for live questions if you'd like, or I will be asking these questions through the Zoom chat and other sources I mentioned. So please enjoy Dr. King's presentation titled A Journey to Understanding Relationships Between Energy and the Economy.
Thank you. You're hearing me well before I get started?
Yep.
Okay. So thank you, Ariana, and thank you, Shruti Ramesh, for inviting me and talking to me initially about being part of your conference. And thank you to Engineers for a Sustainable World and Alyssa for arranging this. A lot of what I'll talk about today is in the context of me trying to understand the role of energy in the economy over the last decade or so now that I've been researching here at the University of Texas, and I have mechanical engineering degrees here from the University of Texas at Austin also. So I worked for a startup company, and then I quit that to get back into understand energy and its role in the economy. So I've completed a book. It's not out yet. So on the right is the book, hopeful cover and title, and that'll be out this fall. So if you're interested, you can look that up later this fall and contact me later. So in thinking about your conference here, just looking at the website for Engineers for a Sustainable World, the mission, as stated, is as an international nonprofit network of students and professionals united by a shared passion for technical sustainability, right? So you can try to understand what that word means. It's a network of people to build a better world through hands-on projects. This is what engineers often like to work on: get your hands dirty, build something, make something work. So what kind of projects does ESW pursue? Still on the website. ESW supports any project that seeks to address one or more UN Sustainable Development Goal targets. I'll give some examples of those. Our project should be measurable, realistic, and timely. So when we think about this, we can think about how do targets get developed, where do they come from, what's measurable, and how would we have any idea about what is realistic or not? Is a target realistic or is it not? What's the difference between technical sustainability and economic or social feasibility? So here's just a list of the UN Sustainable Development Goals. There are 17 of them that they have nice summaries on their website for. But let's just look at a few that might relate more closely to energy and environmental impacts. So number 7 is affordable clean energy. Here's an example of one of the targets, 7.3. Talks about doubling the rate of improvement in energy efficiency. And they give metrics or indicators for some of these. So an indicator in this case is energy intensity, the total energy consumed divided by the gross domestic product of a country or the world. So improvement in energy efficiency would be a decline actually in this measure. And we'll approach this later in the talk. Number 8, decent work in economic growth. So most of the time people say to have a sustainable economy, we need some form of economic growth. We can think about that question during the presentation. Indicators, can we decouple economic growth from environmental impacts, degradation, total materials use? So that's what material footprint here as an indicator is, the total mass of resources, say, extracted from the environment on a given year. Number 12 is another example, responsible consumption and production. So yeah, you could ask yourself, what does the word responsible mean? In general, it's looking to reduce waste generation through prevention, recycling, reduction, reuse. So this is the classic 3 Rs, plus as well as just reducing generation through preventing the use of materials. And 13, we can think about climate goals. So this is kind of a very long time horizon, although the pressures to make efforts are now increasingly becoming more short-term to start to make progress. We can think of this as lowering carbon emissions, or in the extreme engineering sense, actually extracting carbon dioxide from the environment and injecting it underground. So these are 4 of the 17 that are examples you can keep in mind, and that we'll approach a couple more times throughout the presentation. So the idea of looking at these is to think, what are the linkages between societal goals or economic goals, reasons we might come up with to do one thing or another, and build one technology or another. So do we understand how there are linkages between these societal goals and the actual technologies that we make? So what's the linkage between being sustainable and having a digital conference, for example? So below in the right-hand corner is a picture I took when I was traveling about over a decade ago in Tibet. And this is an interesting example of the use of energy technology. On the lower left of the image is a pile of yak dung. So this is a high mountain lake in the summer, and there are nomadic yak herders that collect the yak dung and use this for heat and cooking. On the right next to them are solar panels. So this is one of the oldest energy resources, in this case animal dung, dried animal dung, right next to one of the most modern energy resources or energy technologies, solar photovoltaics. An important point to take away from this, and when you look at, if you were to look at global energy consumption data, is when we invent a new energy technology, we have not yet really removed the use of a previous technology. We have oil, we consume a lot of oil now, but we still consume the increasing amounts of coal. We have solar photovoltaics, but we still consume natural gas for power generation. So we tend to try to extract as much energy as we can, and this is potentially in conflict with environmental and sustainable goals. So there are goals that we can come up with, and largely these are words, phrases. We may have metrics like energy intensity, and these are informed by models that tell us how to calculate these metrics. They're also informed by theories that tell us what these metrics might mean to us. It's one thing to look at the numbers. It's another thing to know how to interpret them or what they mean. So how do we relate goals to stuff that we can measure in a more, let's just say, objective sense? Physical resources, machines, people. I know how many cars there are, how many houses there are, for example. How do we relate these things to each other? This is kind of the way of linking energy in the economy. So think about machines that consume energy, and how does this affect the economy in general, economic growth, economic distribution, etc. So what we measure is one thing. The meaning we give to the measurements is another. This is where more abstract thinking comes in, theory. And so now we will go down the rabbit hole just a little bit. So just to give you a feel for how what we perceive might be different than what is actually occurring in the world, just stare at the screen here for, I'm going to leave it up for 10 or 15 seconds. Look at the white cross in the center. So we're all looking at our individual screens. So stare at the white cross and try not to let your eyes roam around a bit. I'm going to hold it here for just a couple more seconds and then move it away. And now I've moved it away. And what you should have seen if you're not a colorblind person is we had a reverse color image of the Texas flag. There was a green on the bottom, an orange color on the left, and when I moved it away to this white screen, you will see a residual image of the Texas flag in its normal color. So since I'm here in Texas, I can show the Texas flag, in which we'd have blue on the left with a white star, red bar at the bottom, and a white bar on top. So the interesting thing here is that when I move away the reverse color image of the flag, your mind experiences a red stripe at the bottom, but there actually does not exist a red stripe that you're experiencing. So if I go back to here, this is the slide at which I moved to, at which you would have experienced the correct color image Texas flag. So the red stripe is not actually there in the environment. It's not actually there observed, but your mind perceives it. Your mind essentially has a model of what it thinks the world is, and it perceives things in the world, and it converts these into meaning or interpretation in your head. So that's just kind of an optical and mind game, but we can translate this to the economy. If I just take away the red stripe, and I rephrase this, I can say that each one of us is experiencing an economy. We go do things, we buy things at the grocery store, maybe we own a car, we pay rent in our apartment. So each of us is experiencing an economy, but there does not exist an economy that you are experiencing, meaning there's not just one economy that everybody experiences and agrees upon what it is and what's going on and why it should be doing one thing or another, or what the rules should be, what the goals should be. So multiple people experience economic activity, but there's not a single economic experience. And this is why there's disagreement about energy and the economy and what sustainability might mean. So I showed you this on the lower left, which is a reverse color image Texas flag, and you constructed this in your head. I've been told some colorblind people reconstruct something that they still perceive as blue and red, and some maybe others. So this is like saying we observe these kinds of physical items. We can observe barrels of oil. We can count these carbon dioxide emissions going into the atmosphere. We can count how many people there are on the planet. We can calculate the number of machines and cars or air conditioners. And we can estimate natural resources. We may not know exactly how much is out there, like how much oil or coal or natural gas is in the ground, but we have ways to try to estimate these, and some are more objective than others. But we construct these other concepts, these higher level concepts we might call emergent concepts, concepts like GDP or gross domestic product, concepts like energy. So we had to invent, or scientists had to invent the concept of energy in the first place. It's not something we just found lying around. They had to come up with the idea of, say, the first law of thermodynamics is the conservation of energy. We come up with ideas of value, social equity, and sustainability. So these are all a little bit more nebulous, and we try to understand how these relate to things that are a bit more objective to look at. So how can we bridge these different ways of thinking? So we can try to understand the context of what we hear, what we might hear on the news, we might hear on what we might see in a Twitter feed, we might hear in a newspaper or on a video podcast or on the evening news. So what do we hear about energy and the economy, and how can we try to understand what people are telling us? So one way is to think about two axes here. There's an energy axis and an economic axis, and there's, in some sense, extreme viewpoints we might perceive on each end of these two axes. For the energy axis, we kind of have fossil fuels on one side and renewable energy on the other side. There might be advocates for fossil fuels and renewable energy use, and they might use the same types of arguments, which is this is the best way to foster economic growth. This is the best way to foster economic equality. You might have the same exact arguments for one or the other, and it might be confusing as to why they could use the same arguments to promote what seemingly are quite different types of resources and quite different types of technologies that have different environmental impacts and different life cycles and even different ways of employing people to pursue them. We also have the economic axis, and the extreme endpoints of this can be seen as techno-optimism on one hand and techno-realism on the other hand. So techno-optimism could be the perspective of infinite substitutability. This would be like saying, yeah, okay, maybe we'll run out of oil someday, or we won't be able to afford to extract it, but we'll have some substitutes that are just as fine. We can produce biofuels to substitute for liquid fuels. We can make alternative liquid fuels out of base building blocks like carbon dioxide and water, or we can move to electric vehicles. So there's the view of infinite substitutability for technology to essentially solve whatever societal problem we need and to solve whatever problem might exist in order to grow the economy. On the other side is techno-realism, which takes into account at its core the idea that the Earth is finite for the moment, at least for all of human history, almost practically all of human history. We've resided our economy on Earth. We certainly sent satellites into space, and we've sent probes outside of the Earth's orbit. But for the most part, economic activity has occurred on Earth. The techno-realists might also fundamentally account for physical laws in thinking about the economy, like the first and second law of thermodynamics, physical resource constraints. And I'll give you some views of that going forward. So what are some examples of things you might hear anytime you read a book, anytime you read an article, or read a blog or a tweet? where might it fit on any one of these? Where might it fit within these two axes? One example in the upper left here is Alex Epstein's book. So I've got the Epstein book, of course. The Moral Case for Fossil Fuels. This book title is pretty much exactly what the book is about. And here's a quote from that book. In fact, modern solar and wind technology do not produce reliable energy, period. Making emphatic statement, wind and solar technology are not good. The book is promoting fossil fuels and saying this is the best way for human prosperity. It's essentially the premise of the book. You can find a quote that pretty much says the exact opposite out there. Here's a quote from a Public Service Commission chairman in Missouri. He states, "It is very clear that there is a worldwide comprehensive trend towards renewable energy, including wind energy, and that is because it is cheap, it is green, it is reliable, and it is safe." So one says renewable energy is unreliable, one says renewable energy is reliable, and the rest of us are there to try to make sense of why people could say the exact opposite thing. Is one of them wrong? Are they both wrong? Are they both right? You can ask a question on this if you'd like in the question and answer session. Another view here, and I'll put one example here for the techno-realism view from Tim Jackson's Prosperity Without Growth. This is a good book to read if you want to understand a little bit of the higher level ideas of maybe this techno-realistic standpoint. So what he says here in this example, so he's talking about decoupling. This was one of the example sustainable development goals, trying to decouple economic growth from environmental degradation. So what he says here is that what it comes down to is whether or not it's possible to implement this potential for decoupling, this potential to decoupling of economic growth from environmental impact. Is this massive technological transformation possible in our kinds of society? And what he means by our kind of society is the way we structure the economy right now, capitalism, the way we promote profits, the way the tax laws and the way the social structures are set up. And the answer suggested in his book is no. He's clear on this. It is highly unlikely we will be able to decouple fast enough to remain within environmental limits, say climate change, or ultimately avoid resource constraints. That would then impose other kinds of constraints, and we would have to react to these. So this is kind of a techno-realism approach. It might be for renewables in the sense of going low carbon, but not thinking that renewables energy is going to solve all the social and economic problems that we might want. So one of the major takeaways here is disagreements along the axis of energy. Should we use fossil fuels or renewables, or what mix should we use? Should really be understood in the context of how someone thinks, or whatever the disagreements are, about the economy, and whether they have a techno-optimistic worldview of the economy, or whether they have more of a techno-realistic view of the economy. So we can think about how these are related in this way. Physical laws, like laws of thermodynamics and other kinds of ideas we come up with from observing the world around us. These physical laws and resource constraints describe how we can and use and access energy. Energy is essentially defined by observing the environment and finding patterns. Energy effectively drives and defines our economy. If you want to have economic activity, you have to consume energy and take it from one form and convert it to another with heat dissipation along the way. In turn, economics informs policy. Economics has some theories or models behind it, and these are used to project what might happen if you change from one policy to another. And policy affects social outcomes. So if we think about these in a shorthand, energy drives the economy. Economy and its ideas, or the economic ideas, inform policy, and policy affects social outcomes. In turn, the social outcomes can feed back to any one of these areas. Just to stay on the idea of feeding back social outcomes to energy, we can perceive things in politics. Upper part here, we have, I think, then running for president, a picture from then Trump when he was running for president, promoting coal, right? Trump digs coal, is clearly promoting high carbon energy, saying this is a great way to move the economy forward, make America great again, have economic prosperity, and create good jobs. On the right, there are people promoting the Green New Deal, saying this is low carbon energy, we're going to invest in infrastructure, and renewable energy as part of this, and this is the best way to have high paying jobs and grow the economy. Again, two completely different perspectives, or essentially trying to reach the same set of goals, but they have two completely different ways of reaching those goals, at least with regard to the energy system. So how do we make sense of this? Let's just consider high-level basic data on energy and the economy. So that's what the rest of the presentation will focus on. So I'm going to start with this, go to some examples, and then come back to this graph here to explain it. So what this graph is saying is, can we understand something about this pattern of global primary energy use, which is the y-axis? This is the total amount of energy consumed in the world economy that we would count from adding up all of the energy consumed related to oil, natural gas, coal, biomass, hydropower, wind power, geothermal, solar power, everything added together. And this is a rate, so it's in terawatts. So this is a rate of energy use, energy per year, or in this case, average to joules per second in terawatts. We use about 20 terawatts of power on average throughout the year. And the bottom axis, or the x-axis, is global gross domestic product. So this is also a rate. Yeah, think of this as the amount of money, net output of money over the course of a year. So this is a rate of energy compared to a rate of flow of money. And we'll look to try to understand this. So these are basically the two most basic data sets that you would look at to try to understand what's going on, how the economy operates. So the way we can try to think about this is to look to various areas of science to try to understand, in this case, biology. So ever since the 1930s, Max Kleiber had started investigating the relationship between the metabolism of an animal, which is essentially how much food it consumes, and it dissipates this energy in the food to generate heat. So that's the y-axis. And this is a logarithmic plot here. And then the size of the animal, or its mass. They list it as body weight here, or kilograms, along the bottom scale. So the question was, how does metabolism relate to the size of an animal? And the first hypothesis you might come up with is that if I increase the size of an animal, which is to increase the size of its mass, m, that the metabolism B might go up just the same amount. It might scale in the same way, but this turns out not to be the case. So if I have a 10 times heavier animal, that animal does not consume 10 times more energy. What does happen when you plot data across several orders of magnitudes, at least clearly here in this case for warm-blooded animals, you would get that metabolism scales with mass to 3/4 power. So in this case, if I have a 10 times larger massive animal, the metabolism of that animal is only, say, 5.6 times larger than the previous animal. So this means energy consumption of the animal goes up slower than the mass of the animal as it grows. So this is an interesting takeaway. People didn't really understand exactly why this was the case for many decades, and then in the 90s, a group of scientists started looking at this more in depth to try to understand it. And one way they understand this is through understanding the let's just say a mammalian system through its circulatory system. There's a heart, it's got a circulatory system, a set of arteries that go down to capillaries, and this has to deliver oxygen and other nutrients to every cell in the body. So it's a closed system. It's a network, if you will, of blood flowing throughout the body. And you have to apply principles like conservation of flow to it and understand how much energy the heart takes to pump it through the different sized tubes of the circulatory system as it branches out into more and more arteries and veins that are smaller and smaller diameter until you get to near the cells. So they use this principle to derive from first principles that they believe this scaling law would come about. Interestingly, this type of scaling law, or we might call a sublinear scaling law, meaning that the metabolism or energy consumption scales or increases more slowly than the size of an animal. This also holds for ant colonies. So this chart shows examples of plotting the metabolic rate of ant colonies versus their size. And for hunter-gatherer ants, which are the black dotted data points, the mass here is pretty much the mass of the ants themselves. So as I have more ants, they will consume more energy in total for the whole colony, but they will consume more energy in a slower increasing rate compared to the increasing number of ants, or at least the increasing mass of the ants. Interestingly, this also holds for fungus farming ants. So there are ants that collect material in the environment and bring it back into their nest, and they grow a fungus. They collect this material because it has nitrogen content. And then they grow a fungus and they feed off the fungus actually in the nest. And there are different types of fungus farmers that collect different types of materials. And the gray dots here, the open circle dots, represent two different types of fungus farmers. The open circles, which scale roughly to the 0.85 power in terms of their metabolism and mass, are the sort of classic leafcutter ants. And these split apart genetically from the previous version of fungus farmers about 20 million years ago. And so they are a network of collecting resources, bringing it into a nest, growing. So we could think of our own economy, and we can try to imagine how much our own economy does or does not represent the same types of process of resource collection, resource processing, and consumption. So this is quite interesting. And again, the mass of the colony here is not just the mass of the ants themselves. If they're a fungus farmer, it also includes the mass of the fungus. So you have to include both of those to understand this process. One group of researchers performed a pretty interesting study. They have a set of ants in their lab, in an ant colony within their lab environment, which they can measure the metabolic rate and the mass of the ants and run experiments to understand how they scale with each other. And here's an example where they had a scaling of 0.8 in terms of their metabolic rate and colony mass. But the interesting thing they did was they started with a certain number of ants, and then they removed half of the ants. And the open circles represent the data points for when they had 100% of the ants in their test. And after they removed 50% of them, and they attempted to remove 50% equally across ants doing different kinds of tasks, the metabolic scaling ratio held approximately the same. So if I reduce the number of ants by 50%, the metabolic rate of the whole colony did not go down by 50%, it went down by less than 50%, which would be expected from the scaling law. So in some sense, it's as if the 50% of ants that were remaining somehow magically knew that the other ants were no longer there. And a lot of times these types of activities are explained by essentially just looking at your nearest neighbor. The ants can see that there's fewer neighbors around them, and maybe they can move around more than they otherwise would have. There's other explanations of the lower metabolic rate of an ant colony scaling with the number of ants, that as you get more and more ants, there's a higher proportion of ants that stand still, that essentially don't do anything. They sort of wait to do things. And if you're just kind of standing still and waiting to do things, you're not going to consume as much food, and therefore your metabolism will be slower. And this is one way in which this scaling law holds. So this is pretty interesting. This is just basically giving you some insight into adjustments of independent actors or agents, if you will, independent ants and cells in your body, and how they might relate to the entire whole of the body or the entire whole of the ant colony. So essentially animal and ant colony metabolism are telling us there's some sort of scaling relationships here between the energy consumption on the y-axis and the mass and size of the entity on the x-axis. And it's less than linear. Energy consumption grows more slowly than mass, but it's maybe to the 1/2 power, some sort of lower range, maybe. So there's some observed range at which these biological entities are observed. So the global economy, if we look back at our graph, essentially scales like in a similar way to the animals and ant colonies. In that sense, just like an ant colony is a superorganism, so is our economy. So let's look at this. If you look at data from around 1900 to 1970, about 1 unit of global primary energy is consumed for every additional 1 unit of gross domestic product. So this is like a linear scaling. You can ask questions on why this might be a linear scaling during this time versus afterwards. But after the 1970s, essentially after the oil crisis and the United States reaching initial peak oil production in 1970 in Texas, we've since surpassed that in the last few years, but it only until have we surpassed that in the last few years. So after the 1970s, global energy consumption scaled to gross domestic product to roughly the 2/3 power. So here again, energy consumption scales more slowly than the size of the economy, just in the same way as ant colonies and animals. And so we might try to ask ourselves and understand why this is happening. So let's think about this a little bit more. Biology and economic data are essentially telling us the same thing. We have this diminishing returns, if you will, or sublinear scaling law between energy consumption and size. So here's how we can think about this a little bit. For an animal or an ant colony to grow, is to increase its size and mass of cells, or to have more ants in the colony, each additional unit of mass or each existing unit of mass must consume energy at a slower rate. All right, so that's just basically a strict interpretation of the patterns that we've seen. For the economy to grow, at least since we've seen after 1970 in the global sense, the global economy, each additional unit of gross domestic product or capital, like a machine, like a car or a home, must consume energy at a slower rate. So this is the parallel between these two ideas. So let's break this down a little bit more. So let's think about the human body. So we have several types of organs in our body, and each organ operates at a different rate of energy consumption. So let's just take brain and skeletal muscle for examples. Our brain consumes about 240 kilocalories per kilogram per day. So this is the rate of energy consumption, sort of at rest. And skeletal muscle, like the normal muscle that allows us to walk and run and pick up items with our arms, consumes only about 13 kilocalories per kilogram per day. The heart, for example, is one of the most energy intensive organs at 440. So let's think about when the body grows. Everybody looks at babies, and babies are cute to look at because their limbs and head are so out of proportion, right? They have a very large head and very small body. I'm not showing an infant here, but I'm showing a picture of a 2-year-old. So let's think about comparing a 2-year-old and a 25-year-old adult person. So a 2-year-old has a relatively large head, which means its brain inside the head is relatively large compared to the size of its body. So for every 1 kilogram of brain, the brain is about 1 kilogram. For a 2-year-old, has about 12.5 kilograms of total body weight, which means the brain is about 8% of its body weight. So 8% of its body weight is at roughly 240 kilograms per kilogram, kilocalories per kilogram per day, and the rest is at some higher and some lower, but on average, mostly lower energy intensities than that. Once you get to a full-grown person, the brain mass to body mass ratio is approximately 1 to 40, or the brain is only 2 to 3% of the body weight. So the body is much larger, but the brain doesn't have to grow at the same rate as the rest of the body mass. So this is one explanation for why the overall energy intensity, or the overall energy per unit of mass of an animal, in this case humans, can be less as you grow, because when you grow from a 2-year-old to a 25-year-old, you're basically adding mostly muscles and bones. Your organs are already there. They're also growing, but they're just growing at a slower rate than muscles and bones, which don't take as much energy to operate. So this is all without us thinking, right? We're not trying to design a more energy efficient body. There's no conscious effort here. This is, in some sense, a requirement in order to grow. You can't add more high energy intensity pieces. You have to add lower energy intensity pieces at a higher rate. So when we think about this for animals and colonies, we can think about what this would look like on this graph. This is just conceptual on the left, and I'll show some examples of US data on the right. Think about metabolism divided by mass. So how much energy is consumed per unit of mass of the entire body of an animal, the entire human body, for example, or the entire ant colony, relative to its mass. So there would be a downward sloping trend here. So we look at the data in biology, you essentially get a downward sloping trend on this graph. So we can ask if we observe a similar downward sloping trend for energy and economic data, or energy data in the US. So here's an example for the United States. This is cars and light trucks, or light-duty vehicles. On the x-axis is the number of vehicles. There's almost 250 million vehicles in the United States, light-duty vehicles. And on the y-axis is gallons of fuel, or energy consumption per car, if you will. And so this is a downward sloping line. We have more vehicles since 1970. These vehicles are, when we add them all up and add up how much energy they're consuming, in general, this is more energy consumption than in 1970, or certainly the 1980s. But here we just show that as they're increasing in number, each one of them on average has to consume less fuel. So they may or may not be more energy efficient. We'll touch on that later at the end of the talk. But in order to grow since 1970, in this sense, growing the number of vehicles, each vehicle had to consume energy at a slower rate, or at least this is what we observe. Let's go through another example. US households. So it's homes, apartments where people live, how much energy is consumed in each one of these. Here we have readily available data going back a little bit further. So from 1949 to 72, this is an upward sloping trend, which means houses, as I add each additional house, on average, it's consuming more energy than the previous houses. So this is the time of energy abundance. This is a time of great energy abundance in the United States and essentially most of the Western world after World War II. This is really an anomaly in history that energy was this available and this cheap that you could essentially increase it, and we're essentially thwarting this relationship that holds in biology of a decreasing slope in energy per mass or energy per unit. But after 1972, it follows the same trend as in the car example on the previous slide, that the economy in this case, each household added to the end of a network of natural gas pipelines. Each house is on the end of a network of electricity, the electric grid. So each time we want to add a piece to the end of these networks that deliver energy to them, each one of them is essentially forced to consume energy at a slower rate. So we can say that's a downward slope, or we can say it's down and then flat and then down, what have you, but in general, it's a downward sloping trend. So we can think about whether we're consciously doing this or whether this is something we are forced to have to conform to, whether this type of pattern is essentially forced from an evolutionary type of standpoint. So how should we interpret this declining energy per mass of animals, or the declining energy per widget? Should we interpret this as efficiency in terms of getting more output per unit of input? And it can be, but I'm going to tell you not necessarily. A more strict way to interpret this is outside of a major energy surplus, which we witnessed after World War II until the early 1970s. In order to increase energy intake and, let's say, work output, we could say GDP output, or we could say actual physical work output, like in an engineering sense. Each added unit of mass for animals, or each added end-use device, house, each car within the economy, must consume energy at a slower rate. That's essentially the strict interpretation from looking at the data. We somehow have not been able to thwart that process. Now, if given that premise, if each widget, each car, each home has to consume energy at a slower rate, then it's a very natural response to try to increase, excuse me. So if each widget or car has to consume energy at a slower rate, a natural response is to increase its energy efficiency. So if I have a car and I'm not able to consume as much fuel anymore, or I might as well try to get it to drive farther on the same amount of fuel. So this is a natural response. And this is, of course, one of the goals for Sustainable Development Goals, to increase the rate of energy efficiency. So most people think, or I'd say a lot of people think, and probably most is correct here, that energy efficiency leads to less consumption and growth. But this is actually not what happens. And so we're going to end on this concept before going to questions. So the first person to really think of this concept was 150 years ago, William Stanley Jevons. He was a British economist. And in 1866, he wrote a book called The Coal Question. So at this time, the British economy was the most powerful in the world. The British Empire was, the sun, as they say, did not set on the British Empire as it controlled lands across the world. And one of the reasons why they were so powerful is because they had industry powered by coal. They were the first ones to do this, and they had a head start, essentially a leap on every other economy. And they could harvest resources like cotton from India, bring it back to England, turn it into textiles, and sell it at a cheaper price than you could by making it by hand. So everybody realized that coal was a big part of the economic engine of the British economy, and they were wondering, how long is this going to last? How long are we going to have coal? So here's an example chart of data for coal production in the United Kingdom over time. And you can see that it goes up until about 1913. At the beginning of World War I is the peak, and then it declines from there. British coal production is essentially close to zero today. So Jevons was asking his coal question here in 1866, well before the peak in coal extraction rate. And he was trying to wonder, how long is this going to last? How long can England be extracting coal and be essentially a leading economy of the world? Are we going to run out? And so most people thought, well, if I get more efficient at using coal and the steam engines and these kinds of things, the coal will last longer. And he says, no, now that I've thought about it, I did not think that this is the case at all. So here's a couple quotes, and then we'll end. It is wholly a confusion of ideas to suppose that the economical use of fuel, say getting more energy efficient use of fuel, is equivalent to a diminished consumption. The very contrary is the truth. Here he means total consumption of energy in Britain, for example, not energy consumption total of a single device. Another short phrase here, as a rule, new modes of economy will lead to an increase of consumption. So if I get more economic in, let's just say, the design of a steam engine, I'll increase consumption in total. So the reasoning or the rationale for how this occurs is in this slightly longer quote. And again, this is during the peak of industrialization in England. It's all about making hardcore capital and machines, railroads, iron, and turning coal and iron ore into iron and steel. So he says, if the quantity of coal used in a blast furnace, that would be used to make iron, for instance, is diminished in comparison with the yield, the profits of the trade will increase. So he's saying, all right, if I use fewer units of coal to make 1 unit of iron, then I'll lower the cost of iron and I'll be able to make more profits if I were to, say, sell it at the same price. Now, if this is the case, new capital will be attracted and the price of pig iron will fall, but the demand for it will increase. So if I get more efficient at making iron and I can lower the price of iron, people will be able to afford to buy more iron, and they will, and then they'll build more things. So that's why the demand for it will increase. Then he states, eventually the greater number of furnaces will more than make up for the diminished consumption of each. So it's not that each individual foundry, iron foundry, is consuming more energy. It's that you make more and more and more foundries. And the reason you're able to make more and more is that it gets cheaper and cheaper to make the output of the foundry, in this case iron, each time you make a new factory. So you're going to make a new factory that's more efficient, not less efficient than the old one, and therefore the product gets cheaper and you're afforded to be able to make an additional factory, etc. And then when you add up the energy consumed by all of these factories, it ends up to be much greater than just one single foundry or one single factory. So this is the idea of the Jevons paradox. It's named after him. The more efficient you get at individual processes, the more energy consumption you will have in aggregate for the entire economy. So in this sense, efficiency conflicts with the environmental impact of human activity, but it's quite good for economics. If I make things cheaper, people can buy more things. And in general, this correlates with well-being, although if you just keep consuming more and more, you don't necessarily become more happy. So this is not to say that, but it does say that there is some inherent conflict here. We have a sustainable development goal of decreasing energy intensity, decreasing energy per GDP, which would in general make things cheaper to buy. And this might be in conflict with the total aggregate amount of waste, or the total material footprint of human activity. It might also be in conflict with lowering carbon dioxide emissions. If it's cheaper to do more economic activity, because we're improving our use of energy, it might also be cheaper to do activities that release carbon dioxide into the air, and we can do more of those activities. So here's the final slide. Think of the economy as it operates like a superorganism. And so to think of sustainability, we have to consider a few things, or at least when you're learning and thinking, learning in your classes, try to open your mind to think about how economics should incorporate scientific knowledge from other areas like physics and biology. What are the constraints that are seen in physics and biology? How many of these constraints hold for the economy? Do we see patterns in the economy that follow these? And does this help us understand the broader picture of what the economy really is as an entity. The feedback of efficiency and low-cost energy is more growth in consumption, not less. This is the Jevons paradox. We might call it the rebound effect. And at even higher levels, some people would call it the backfire effect. We can also think about how individual energy-consuming activities are distributed and how they add up to the whole, right? Just like our brain and our heart consume a lot more energy per mass than our skeletal muscle, we can think about how this translates to the economy. Some sectors and some economic activities consume more energy or have more CO2 emissions and some less, but they all add up to the whole. And you can't necessarily get rid of the high energy intensive activities in the economy without linking to the lower energy intensity, say, service sectors of the economy. These are all linked together and dependent upon each other. If you want some further insights into some of these ideas, there's some great videos by Nate Hagens, which are called Reality 101 at the University of Minnesota. They called it the Nexus 1. So look up Reality 101, Minnesota Nexus 1 and Nate Hagens on YouTube, and you'll find a series of videos that are quite enlightening on some of these same ideas. And that's the end of my main presentation, so I'll stop here and let you ask for questions. You can see my information on the screen and my website, and hopefully out in the fall 2020, my book will be out if you're interested in following up. So thank you.
Thank you so much. That was awesome. So our first question is, have researchers observed other species besides ants and seen similar trends? Is there a reason that most have observed ants over other species?
All right, so that's a great question to stump me since I'm an engineer here and studying the economy and not a biologist. So my answer, my hypothesis would be yes, they found other examples, but I don't have many other good examples to give you just due to my lack of knowledge. So I've set you up to ask a question that I can't answer. So thanks for the question, because it's a great question, and I hope to understand more of that. Essentially, social insects, or what they call eusocial species, like bees and ants, can exhibit this, but they're not the only ones that have these, in some sense, social qualities. So you would look towards animals that operate as sort of a social cohesive unit to look for these kinds of patterns.
Awesome. So another question says, you showed the UK impact of coal. Do you know how coal production and consumption impacted the US, especially with steam engines?
Well, and certainly in a similar way. Energy consumption and GDP, well, I'll state one thing here. I have some other slides I probably won't get into, but there's an idea that is called useful work, sort of a thermodynamic idea. Useful work is defined as we might think of work if you study thermodynamics. So it is essentially energy consumption times the efficiency of conversion to the final form of mechanical work. And the final forms of mechanical work could be like human muscles or animal muscles doing physical work. It could be the drive that comes out of an internal combustion engine in a car. It can be the electricity that shows up in my house. This can be useful work, as well as some concepts like the high temperature heat and industrial processes. So if I count this useful work, which is essentially the energy in its mechanical form, if you will, at the end of the supply chain, if you count that instead of the primary energy, what the economy is really trying to do is increase the quantity of useful work. And there are several papers that show if you can estimate useful work precisely enough, this essentially has a one-to-one correlation with GDP. This implies that the economy is essentially a heat engine. The economy is trying to do useful work on the environment. It's trying to do work on the environment. So the more useful work there is, the more GDP there is. So in some sense, GDP is a proxy for physical work on the environment. And so the US shows this pattern. The United Kingdom shows this pattern. People have explored this for Austria and Japan as well. And so the hypothesis is that this would hold for the entire economy as well. If you want more insight into that, you can email me and I'll give you some pointers. Good question, though. It's great.
Cool. So a question from the chat is, you mentioned that that efficiency is one interpretation of increasing GDP per unit power use. What are other interpretations?
That's so. I would say essentially the one other interpretation I have is that if you have, I'll call it an energy constraint here. but that's a little bit vague. Essentially, before the 1970s, to produce more energy, I'll just point to oil here as the major growth in energy consumption after World War II. If you look at energy consumption growth after World War II, it's the fastest it ever has been for 30 years, that 30-year period. It's faster in that time period than any time period in the history of human beings, any time we have data. It grows at over 3% a year. This is the only time it's done this. And it's mainly due to an increase in oil consumption. And during this time, the Texas Railroad Commission was essentially the world's first energy cartel. There was so much abundant and affordable energy, oil extraction in Texas, and they had wells drilled to such prolific reservoirs, and essentially the Railroad Commission essentially throttled back how much oil could get produced. So the oil could have come out of the ground faster than it did, but they knew this would destroy the oil industry by lowering prices too much. So imagine a valve, or at least a series of valves on all of these oil wells, and they're at 30% in 1950. And then in 1955, they're at 50%. Then at 1965, they're at 80%, or something like this. So you don't really have to invest much in energy extracting activities in order to get more energy out, because the energy resource was so prolific that you needed very little effort to do this. You need very little extra investment. By the time you got to 1970, the valves were 100% open. You couldn't just produce more oil by turning the valve. You actually had to go out and drill more. You actually had to go out and find more energy resources, not just oil, but other things as well. So it's once that constraint occurred that you now have to invest in energy extraction activities at some coordinated rate with energy consuming activities. And once this coordination has to occur, this is where the scaling law sort of approximates. And this is why you have roughly a linear scaling law, that more energy could be consumed, or the increase in GDP could be equal to the increase in energy consumption before 1970, but after 1970, that no longer was the case. You could only increase GDP by increasing energy consumption at a slower rate. And this has to do with investing in the energy infrastructure extraction system and distribution system in coordination with the energy consuming activities like cars. But before the 1970s, you could just build more cars and not think about how efficient they were, because the oil could come out of the ground to power them without a problem. So it's this coordination problem that forces the scaling law. This is an area of further research, but this is my hypothesis, that it's this coordination of investment that relates to the scaling law. And so each car, for example, has to consume less energy if you want more cars. And then energy efficiency is a response to say, well, if each additional car has to consume less energy, I might as well make it more efficient so that I can drive further. It's a natural response. It's a good question and a deep one, and still not consensus in the literature, probably.
Cool. Our next question is, would it be fair to say that an elephant could never survive operating at the efficiency level of a rodent, just as our modern economy could never survive operating at the efficiency level of the pre-1970 economy? In other words, increased efficiency is a necessary part of growth, and that growth is inevitable with increased efficiency?
I like that statement. I think that's probably a good way to say it. On the biological sense, so there's a book called Scale by Jeffrey West, if you're interested in these ideas. He summarizes a lot of this, some of the ideas I put here. And one of the aspects that they point out in this literature that he and others, Jim Brown, who used to be at the University of New Mexico, that work together, that study these metabolic scaling laws across biology, is that roughly speaking, I guess for animals, there's a almost constant number of heartbeats. I think it's 1.5 billion heartbeats per lifetime. So a mouse has a really high metabolic rate per mass. Its heartbeat is really fast. So it goes through its heartbeats and it doesn't live very long. An elephant lives much longer because its heartbeat's much slower. You could call that more efficient, but by definition, or more strict definition, is that its heartbeat's slower. And it's as what implied by this question, that all of these things are related. The heartbeat is related, the rate, metabolism, the heartbeat, this is all related to the size of the animal. So in my view, economic activity exhibits the exact same patterns. That size, in fact, dictates the rate of energy consumption by all the pieces of the economy the more pieces we have, the slower each one has to operate. So I think the parallel is there.
Really cool. So next, in your opinion, is there a most useful economic worldview to promote sustainability, such as technological advancements, policy, etc.?
Yeah, I suppose I can't remember if you used the word bad. I try not to use the word good or best. I try to look more about what's happening. But in my view, certainly in the context of the last paper I published, which was a new kind of economic model, it inherently has some aspect of the size of the environment or the size of the earth in it. So in my view, if we want to understand long-term economic growth, you need some measure of the size of our environment, or essentially the size of the earth in your model and in your worldview. The alternative is, if you don't have some size in your model, like how much oil do I think there is, or how much forest do I think there is, you're inherently assuming that the size of the environment is infinite. And I have a hard time thinking of that as a good way to understand long-term growth, as well as how the growth of the economy would have to structure itself based upon any constraint. So I think you need some metric of the size of the environment that the economy resides in order to even have a chance at answering the question whether the size of that environment is affecting the economic growth itself. So if I'm interested in saying, is climate change affecting the economy, or is going to renewables going to be a different type of economy than fossil fuels? If I don't have the size of the environment in there, then I don't even know how I could possibly answer that question.
That makes sense. So do you think that oil initiatives, oh, sorry, I think I wrote this question wrong. Do you think that oil industries with sustainable initiatives are sufficient for them to survive, since the US and the world is so dependent on the oil industry as a whole?
This is a question. So a lot of the oil companies it's a good question. Many of the oil companies have come out with statements to try to move to different kinds of business models. I think Shell probably is one of the international oil companies that has some of the more far-reaching statements. So far, the actual movements or investments maybe haven't been in line with those statements, and I think most of the companies recognize this. So they will, in some sense, be forced to move with the rest of the economy. They're adjusting pressures or policies on both ends, pressures of policies on energy companies to change, and pressures from consumers on what they buy or what they might be able to afford to buy, all play a factor. I'm not sure how to answer the full question, other than all the pieces have to fit together in a certain way. I tend not to like statements that say, well, we consume a lot of oil today, and to be prosperous in the future, we have to continue to consume a lot of oil. Just to say, for example, fossil fuels, maybe more generically. We're kind of really between a rock and a hard place. It is a true enough statement to say that the lifestyle we lead now is derived from fossil fuel consumption, and if we got rid of it tomorrow, that would be too dramatic for the economy to adjust. But that's kind of a straw man argument. That's not the real argument. The question is, can we go to something where we have less carbon emissions, let's say? If the fossil fuel industries play a part in that, they still can. Granted, any company doesn't have to be defined as a fossil company or not. They could adjust, or at least in theory they can adjust. But one of the arguments that some fossil companies put out is that investors don't want them to be a diverse company. They want them to be an oil company because they want to diversify their portfolio. And I need some oil company and some renewables and some pharma or whatever I need. And if you change the way you are as a company and make it more complex to figure out what you are, then it makes it harder for investors to understand what to do. So it's pretty complex, to state it mildly. But it is hard. I mean, what we observe, it is hard for one reason or another for the economy to, for individual companies and consumers to essentially collectively consume less or collectively do things that reduce CO2 emissions. I believe these things are related to evolution and fundamental issues of competition, and maybe unconscious concepts of essentially growing and trying to do more useful work on the environment, just like an animal might grow or an ecosystem might grow. It's not consciously thinking about growing, but in some sense, that's just what it does.
Interesting. There's another question that kind of connects to that. It's that, is there some solution to the Jevons paradox? Is it just a matter of raising awareness or trying to completely overturn something like consumption culture at large?
Right, there's a lot of talk on, say, how do you overturn consumption culture? And I think this gets to my last statement. A nice statement from Nate Hagens, who I referred to at the end. Collectively, in some sense, we're at fault for, say, increasing carbon emissions, but individually, none of us is to blame. So none of us are thinking that we're causing some problem, yet we're all trying to get a job or increase our salary or something like this. And when you add up all these individual pieces, this is essentially the driver behind Jevons paradox. So there are, I think, no good examples of, let's just say, a system, an ecosystem, right? If I have a tropical rainforest, there's nobody imposing any kind of rule on all of the animals and organisms living within the tropical rainforest to stop consuming. They basically consume up to the limit that they can, given the rainfall and the sunlight that falls onto the system. In that sense, our economy is just trying to do the same thing. The one way you could just grow until we can't. So there's no other example of, we would have, of the system imposing a constraint on itself. That's essentially what we're asking. We've created this economic system. We're living organisms. We operate by some conscious and unconscious decisions. And are we going to impose a constraint on ourselves collectively? Some people use the Montreal Protocol, which limited fluorocarbons and into the atmosphere that caused ozone depletion, high-level ozone depletion, as that's sort of the one treaty that every country signed on to in a global constraint, if you will, on certain types of chemicals manufacturing. But that was relatively small compared to the global carbon emissions issue that we might be dealing with. So the solutions were available and relatively small impact to the economy. For carbon, it's a much different story. So it's a great question. I don't have the answer. From a stepping back from just sort of a systems and biological perspective, I can look at the patterns and say, yeah, that makes sense. We're just like every other, the economy is just like every other superorganism. How do we prevent it from acting just like every other superorganism? It's not clear it's possible, but we can certainly think about it.
Thanks. So the last question that I have here, there's still a little bit more time if anyone wants to submit more questions, but the last one I have is, how do efficiency trends in Western countries compare to rapidly developing trends in countries such as India and China?
Right. Well, we're certainly more efficient, and you would expect developing countries generally have faster rates of energy efficiency. In some sense, just because they start from a less efficient starting point. So if you're starting, the same thing happened in the US or the UK. We all started from relatively, let's just say, inefficient, high energy per GDP. As you grow, you have to grow different parts of your economy, just like we grow different parts of our body. And in some sense, the higher energy efficiency comes from that. So we would expect increasing energy efficiency in developing countries, but I would also expect the same pattern, which is they'd still consume more energy, they'd still consume more resources, and they'd still, say, increase population, but at perhaps a slower rate. So it's difficult, but I think we can't get trapped into thinking about the linkage of efficiency and actual total consumption. I'm going to go to this chart, which kind of may be insightful to this question. This is one of my favorite charts. This shows data for England and the United Kingdom from the year 1300, yes, to 2008. This is essentially like we had the story of the size of the human brain when it's a baby versus an adult. In some sense, we can view this as the size equivalent the size of the energy system, and since agriculture. So pre-industrial, the energy system is essentially agriculture. Biomass feeds animals, they do work. They feed people, that does work. And so these are different categories of end uses of energy for physical labor or power, physical power. So in a pre-industrial sense, before 1700, something about 60% of the economy was the energy system. After we discovered the steam engine and started using coal, this percentage or relative size of the energy system, just like the relative size of your heart or brain, decreased. Now, it wasn't that our bodies got smaller when we were after 2-year-olds, our bodies got bigger, just like the economy of the UK and the US got bigger, but the relative size of the energy system got smaller, and this is because the energy system became so productive with steam engines. It could actually do more physical work. So this is the really long-term perspective to see the transition from an agrarian to a fossil fuel society, and this provides the context for trying to understand how to go to a renewable system. Is this percentage of spending on energy or the relative size of the energy system, would it go up? And if it did go up again, would this mean we have to go back to some organization that would have existed in the past?
So we have two final questions. One is about the GDP and energy usage graph. And they're wondering if there's a noticeable dip from the advent of the internet, just as there is a noticeable dip from the energy crisis of the 1970s.
Right, yeah. This is a, let's see if I can answer it. So there's not, I think it's probably not that noticeable from the internet, at least at the global scale. At the country level scale, people might see things. Most of the discussion of, let's just see why the economy grows, or the conventional way of thinking, if you will, about how the economy grows is, do you have more capital in machines and houses or cars? And so there's capital. More capital means a larger economy. Do I have more people working or labor? If I have more people working, then this also is a factor which leads towards a larger economy. And so if you account for those two things, I try to think of other ways outside of this way of thinking, but if you account for those two things and you look at what the actual data are for GDP, there is about half of all economic growth left over to explain. So this is called total factor productivity in literature, so or maybe sometimes just productivity. And so some people use this as a measure to try to understand the impact of things like the internet. And they might see a bump up in this total factor productivity in the 90s with computers in general, and then a little bit later with the internet. But in general, this productivity measure is lower than it was, say, in the 1950s and 1960s. And so economists are sort of, in some sense, confused and trying to think about why this is the case. Some people think that these technologies, the internet and computers, are just not as productive as things like combustion engines and combustion turbines were in the past in terms of their influence on the economy. Some economists think that we just don't value them properly. We're undercounting the value of free stuff on the internet. And if we did it properly, then GDP would look much higher. I haven't thought enough about that to understand if I like this argument or not. But I'll go back to this useful work idea. The people studying this idea and looking at the actual increase in energy efficiency of, let's just say, all devices in the economy, that is the most exact or the most accurate description of this total factor productivity measurement that I've seen. So in some sense, economic growth can happen by, so useful work equals energy consumption times efficiency. So therefore, if that matches 1-to-1 with GDP, I can increase GDP by increasing energy consumption or increasing efficiency. If I have more energy, then sure, great. But if I can't consume more energy, I can try to increase energy efficiency, and that also translates to growth. Now, the second law of thermodynamics tells us I can't increase efficiency forever. The finite Earth perspective says I can't increase my energy consumption forever. So this sort of techno-realistic view says I'm a scientist, and those two things are as real and as accurate to me as anything else. So therefore, I should expect that I can't grow the economy forever. So I need to put that in my framework. I got around your question. That wasn't exactly your question, but so the short answer is people see some evidence for growth from computers and the internet, but some people claim it's not as big as it should be.
Thank you. So our last question is, they've said, we've established that increased efficiency increases whole consumption. Previously, I would have considered increased efficiency as being more sustainable. Now I'm thinking otherwise. should we even include efficiency as a way to be more sustainable?
Yeah, so you got the point I was trying to impress, and one of the reasons I brought it up is because I think this point is not brought up early enough in people's education. So I didn't really become cognizant of this concept until after graduate school, and I think it's important for people to grapple with. It's not there to make people angry or happy or any in general, just it's in the data. It appears to be in the data. People disagree on it. That's my answer. The question implied what my answer would be. So you're asking me, so the answer is yes, I don't think efficiency is more sustainable in a environmental sense. Now, if I somehow as a system could constrain my total consumption and say, you know, I'm just not allowed to emit, I'm going to actually decrease CO2 emissions per year. I'm somehow going to impose this constraint. If you really held to that constraint, then you could say, fine, now I'm going to try to increase efficiency as much as I possibly can, because that's going to give me the as increased lifestyle as possible. But it would only be, in some sense, sustainable because I'm imposing this other higher level constraint. And that's what is, I don't even know if it's possible, but the more people talk about it, I think the better we can make that possibility happen if we wanted to, and at least we can understand it. At least I like people to understand this trade-off so that they just don't kind of go off and think that there's going to be no implication of higher efficiency without some other constraint. I just don't think we have evidence for it. People disagree on this pretty vehemently. So.
Well, thank you so much, Dr. King. I think I personally enjoyed this a lot, and I think everyone else did too. So to everyone in the audience, our next event is the Earth Hacks competition. So if you signed up for that, you can check back into this Zoom room at 2:30 Eastern time. If not, check out some of the pre-recorded content that we have on YouTube, and then you can check back here to this Zoom room at 4:30 to see who won our campus challenge. Thanks, everyone.
Thank you, Mariana.